Okay, let's talk about the use of the rules of quantum numbers. The rules ultimately have to do with the restrictions that I mentioned in the previous videos. The fact that n can be at the very least a value of 1 and it can go up in integral numbers. The fact that L can go from 0 up to n minus 1, and n minus 1 becomes the restriction. That's the maximum value that L can be. And in essence, we're going to have to look for what that number is before we start looking at the possibilities for L. And once we know the values for L, we can actually determine the range for M sub L, which goes from negative L up to plus L. So let's take a look at the various energy levels and see what happens in terms of the picture being developed. If we start at the very beginning, energy level 1, the only possibility is for L to go from, well, if n equals 1, 1 minus 1 is 0, so L has no choice but to be simply 0. That's the only possibility for it, because L can be greater or equal to 0, or it could be less or equal to 0, and since n minus 1 is 0, that locks L as being 0. And also, since L is 0, negative L and plus L are literally the same number, simply 0. And also, what this tells us is the type of orbital that we're dealing with. Since L equals 0, that number is associated with an s orbital. So the notation that we use is given by the first two numbers. The number 1 for n, which we have placed right here, so that's the number 1 for the principal quantum number. And instead of writing the number for L, we write the associated orbital for which the number is given. So L equals 0 implies that we have an s orbital here. All right, now that's basically the story for the first energy level. So what this tells us is that in the first energy level, all we have is a 1s orbital. That's it. So let's take a look now at the second energy level, where n equals 2. If n equals 2, this tells us that 2 minus 1 is 1. So now L can go from 0 up to 1. So let's start with 0. For 0, we know that M sub L will also have to be 0. And we know that the notation will have to be now 2s. S because L equals 0, and 2 because the principal quantum number is 2. But we still have the possibility that L could go up to 1. And for 1, here's where something interesting starts happening. If L equals 1, M sub L can go from minus 1 up to plus 1. So you have some possibilities. And also, because the value of L is 1, we're now dealing with a p orbital. So notice the notation, we're still on the second energy level, but we're now dealing with a p orbital. So this is the 2p orbital present in the second energy level, and the values of M sub L can go from negative 1 up to plus 1. So these are all the possibilities. So what this tells us is that in the second energy level, we have one 2s orbital, and we have three 2p orbitals present within it. All right, let's take a look at the third energy level. In the third energy level, we can go up to a value of L of 3 minus 1, in other words, 2. So we can go from 0 to 1 to 2, and each one of these things represents a possibility for the value of L. If L is 0, M sub L has to be 0, and if L is 0, we're dealing with an s orbital. In the third energy level, this will have to be the 3s orbital. If L equals 1, well, we're dealing in that case with negative 1, 0, and plus 1 values for M sub L. But if L equals 1, we're dealing with a p orbital. And since this is the third energy level, this is specifically the 3p orbital. But there is a set of 3 of those 3p orbitals present. We also can go up to a value of 2, because remember, L can go as far as n minus 1, and since n is 3, 2 is as far as we can go. Okay, so for a value of 2 equaling L, we know that the orbital in question is the d orbital, and since this is the third energy level, the 3d orbital is what we're dealing with. And since L equals 2 for the orbitals, that means that we can go from negative 2 up to plus 2, meaning that we have 5 different options for the orbitals. What I want you to kind of notice as we're going through this is the fact that in the first energy level, all you have is the 1s orbital. In the second energy level, what you have is the 2s and the 2p orbitals. And on the third energy level, what you have is s, p, and d orbitals all present within it. You have one set of s orbitals, three sets of p, and five sets of d orbitals in the third energy level. All right, let's go up to the fourth energy level. Here, L can go as far as 4 minus 1, which is equal to 3. So you could start with 0, in which case m sub L is 0, in which case you're dealing with a 4s orbital. You can move on to L equals 1, in which case you're dealing with a 4p orbital, and you have three sets of 4p orbitals present. You could go up to L equals 2, in which case you have five sets of 4d orbitals present. Or you could go all the way up to L equals 3. And for L equals 3, you're now dealing with an f orbital, specifically the 4f orbital, since we're dealing with the fourth energy level. And this means that we have 7 f orbitals present in this particular set, and all of them, the s, the p's, the d's, and the f's, are present as long as you are at least in the fourth energy level within an atom. All right, now for 5, what I'm going to do is kind of switch the picture a little bit. As opposed to kind of looking at all the possibilities of what we have present, what I'm going to do is kind of give you numbers. Numbers for n, numbers for L, and numbers for m sub L. And what I'm going to ask is if the quantum number set is allowed or not. And we need to use the restrictions given here in the red, blue, and pink boxes for n, L, and m sub L. So looking at the values, okay, so first we take a look at the value of n equals 5. If n equals 5, we know via the second equation here that L can go up to a value of 4. So we look at the value of L. L is below 4, so we are okay, that checks out. Now, since L is 3 specifically, that means that m sub L has to go from minus 3 to plus 3. And it so has said that m sub L equaling negative 2 falls within that range. So this is indeed allowed. Now let's take a look at another set. N equals 3. If n equals 3, we know that L can go up to 2. And look at the value of L, L is 0. So that's definitely below 2, so we're totally fine with that value. So the first two are okay. If L equals 0 though, m sub L can go from negative 0 to positive 0. In other words, m sub L can only be 0. And since m sub L here is not 0, what this is telling you is that this set of quantum numbers is not allowed. This is not an actual set. Okay, let's continue with the process. If n equals 2, that means that L can go up to 2 minus 1, which is L equals 1. And looking at this thing, we see that, oh, well, L is not 1, and in fact is greater than 1. That means that this is not allowed. Automatically, without even looking at m sub L, this is disqualified for being a correct set of quantum numbers. All right, here goes another one. If n equals 6, we know that L can go up to a value of 5. All right, the value of L is exactly 5, so that's perfect. That's allowed. If L is 5, m sub L can go from negative 5 to plus 5, and negative 4 falls within that range. So this is indeed an allowed set of quantum numbers. All right, we'll do one more. N equals 7. If n equals 7, L can go up to a value of 7 minus 1 or 6. The actual value of L is below the value of 6, so this actually works out. But L being 2 means that m sub L can go from negative 2 up to plus 2. And the value of m sub L is indeed plus 2, so this is allowed. Alright, so this is the type of question that you might expect to see on upcoming homeworks or exams. It's basically a means for you to kind of see whether quantum numbers are, making sense in terms of the depiction of the electron by following these restrictions. Alright, so in the next video we're going to move on to talking about radial nodes, how to draw these particular orbitals, including radial nodes, and then we'll start talking about the spin quantum number. Okay, see you in the next video.